enjoy learning!
Hello everyone! Welcome to week 2 of our general mathematics subject. I am your mathematics teacher, Sir Jason D. Reyes. Sit back, relax, and enjoy learning! At the end of the lesson, students are able to first, represent real-life situations using rational functions. Second, distinguishes rational function, rational equation, and rational inequality. Third, solves rational equations and inequalities. Fourth, represents a rational function through its A. Table of values, B. Graph, and C. Equation, and lastly, finds the domain and range of a rational function. Our topic for week 2 is about rational functions, equations, and inequalities. Lesson 1. Representing real-life situations using rational functions. Definition of rational function. A rational function, r of x, is a function in the form of r of x is equal to p of x all over q of x, where p of x and q of x are polynomial functions and the q of x is not equal to 0. The domain of the r of x is a set of real numbers such that q of x is not 0. Examples of rational functions. The following are examples of rational functions. First, r of x equals x cubed minus 1 all over x plus 1. And x should not be equal to negative 1. Both numerator and denominator are polynomial functions. Denominator has restriction because it should not be equal to 0. Second example, function of x equals 1 over x where x is not equal to 0. The numerator 1 is a polynomial function with a degree 0. The denominator is a polynomial function and it must not be equal to 0. So as you can see, the restriction should, denominator should not be equal to 0. So the value of x is not equal to negative 1 and x is not equal to 0. There are different scenarios of real-world relationships that can be modeled by rational functions. Let us take the following examples. Example number 1. The local government unit allotted a budget of 100,000 for the feeding program in the daycare center. The amount will be divided equally to all the pupils in the daycare center. Write an equation showing the relationship of the allotted amount per pupil represented by the function of x versus the total number of children represented by x. So this will be our table. Showing the relationship in tabular form, we will arrive at, so we have two components, the number of children, which is the x, and the allotted amount per children. So we have 10, 20, 50, 100, and 200. So the allocated amount are as follows: 10,000, 5,000, 2,000, 1,000, and 500. Notice that as the number of children increase, the amount allocated per child decrease. So as you can see, when the number of children increases, the allocated money increases. So in writing a representation, we will arrive at the following equation. So f of x is equal to 100,000 divided by x, where x is the number of children. Example number 2. Suppose a benefactor wants to supplement the budget allotted for each child by donating additional 600 pesos per child. If h of x represents the new amount allotted per child, construct a function representing the relationship. So, in solving this problem, we should determine the number of children and the allocated amount per child. So, as you can see, we have a total number of children, 10, 20, 50, 100, and 200. So, the allocated amount per children are as follows. So for the 10 children, it will be 10,000 plus 650. So 650 is for the additional child. 20, 5,000 plus 650. So 650 is for the additional child also. For 50, it will be 2,000 plus 650 pesos. For 100, it will be 1,000 plus 650 pesos. And for 200, it will be 500 plus 650 pesos. So as you can see in the table, we can conclude that the representation of the rational function is a g of x equals 100,000 divided by x, which is the number of child, plus 650. So 650 is the amount for the additional child. Example number 3. A car is to travel a distance of 70 kilometers. Express the velocity v as a function of travel time t in hours. So let us first show the relationship using a table. Remember that as time increases in traveling, the velocity or the speed of a car will decrease. So we have also two components, the time and the velocity. So time is in terms of hours. So we have 1 hour, 2 hour, 3 hours, 5 hours, and 10 hours. And the velocity, which is in terms of kilometer per hour, are as follows: 70, 35, 23.33, 14, and 7. So based on the table, we can conclude that the function b of t equals 70 over t can represent v as a function of t. Lesson 2, Rational Functions, Equations, and Inequalities. The job advertisement shows the need to conduct a census. Census is important because it will serve as the basis for planning for the future, such as public safety, infrastructures like hospitals and schools, and improving homes in the neighborhood. This also serves as the basis in predicting the number of people who need help in times of crisis. However, in finding enumerators who will conduct the census, there are different qualifications needed, and some of those are the age retirement and educational attainment. To represent it mathematically, the use of inequality symbol was employed. However, the salary was also mentioned, and to be able to represent it, equality symbol is used. At this section, we will compare rational expressions using equality and inequality symbols. Thus, we will further classify the differences among rational equation, rational inequality, and rational functions. So in this lesson, we will study about the rational equation, rational inequality, and rational function. We will differentiate the three terms from each other. So rational equation is an equation involving rational expressions. So this is an example. X plus 4 all over x minus 1 equals 1/5. So as you can see, we have a rational expression and we have the equal symbol. So that will be the rational equation. So for rational inequality, it is an inequality involving rational expressions. So we have rational expressions and the inequality symbol, which is greater than. So it can also be less than. So that will be for our rational inequality. For rational function, it is a function of the form f of x equals p of x all over q of x, where p of x and q of x are polynomial functions and the q of x is not the zero of the function. So this is an example. Function of x equals x squared plus 6x plus 8 all over x plus 4. As you can see, we have the rational expression and we have the function which conclude the rational function. To further understand about rational equation, rational inequality, and rational functions, here are some of other examples. First example, x plus 5 all over x minus 1 equals y. So, this is an example of rational function because the symbol y is also a representation of function of x or the symbol which is the function of x. So, meaning to say, y is the same as the function of x. So, if you see a y, it is also a function. Example number 2. Square root of 2 all over x plus 1 is less than or equal to 3. So, none of this is a rational expression because square root of 2 over x plus 1 is not a rational expression. So, a rational equation, inequality, and function should be free from radicals. So, square root is a radical. So, it is not a rational equation, rational inequality, and not a rational function. Lesson number 3, solving rational equations and inequalities. Rational equation is an equation containing at least one rational expression with a polynomial in the numerator and denominator. It can be used to solve a variety of problems that involve rate, time, and work. Using rational expressions and equations, it can help us to answer questions about how to combine workers or machines to complete a job on schedule. So let us use the previous activity to discuss and deepen your knowledge and skills in solving rational equation. The first thing to be in your mind in solving rational equation is to eliminate all the fractions. Illustrative example number 1. Okay, let us solve for 2 over x squared minus 1 minus 1 over x minus 1 equals 1/2. So, the first step we are going to do is to find the least common denominator. So, given this rational equation, the LCD of the given fractions is 2 times x minus 1 and x plus 1. So, we already knew this because we discussed it in our junior high school mathematics. Step 2, you need to multiply the LCD to both sides of the equation to eliminate the fractions. You can also apply cross multiplication if and only if you have one fraction equal to one fraction. That is, if the fractions are proportional. In this case, you cannot use the cross multiplication unless you simplify the left equation into a single fraction. So, we need to multiply our LCD to the original equation. Okay? Let's multiply. So, multiply the LCD, which is 2 times x minus 1 times x plus 1 times 2 all over x squared minus 1 minus 1 over x minus 1 equals to 1/2. So, after multiplying the least common denominator with the original equation, we will proceed to step 3. You simplify the resulting equation using the distributive property and then combine all like terms. So, we will now simplify. So, 2 times 2 minus 2 times quantity x plus 1 equals x minus 1 times x plus 1. After that, we simplify using the distributive property. So, 2 times 2 equals 4 minus negative 2 times x, which is negative 2x. Negative 2 times positive 1, which is negative 2. Copy the equal sign, equals. Then, multiply x minus 1 times x plus 1. So, x times x is equals to x squared. X times positive 1 is positive x. Negative 1 times x is negative x. So, we will just cancel negative x and positive x. Then, negative 1 times 1 is negative 1. Then, simplify. So, x squared plus 2x minus 3 is equal to 0. So, after we simplified, we proceed to step 4. You need to solve the simplified equation to find the values of x. In this case, we need to get the equation equal to 0 and solve by factoring. So we need to factor the equation x squared plus 2x minus 3 is equal to 0. So factoring, we get x plus 3 times x minus 1 is equal to 0. So in factoring, we should know a number which has a sum of 2 and a product of negative 3. So as you can see, the value is 3 and negative 1. So 3 plus negative 1, we have the sum of the roots, which is 2, and the product of the roots, which is 3 times negative 1, which is negative 3. So after that, find the zeros of the function. So equate x plus 3 and x minus 1 to 0. So x plus 3 is equal to 0 or x minus 1 is equal to 0. So the value of x are x equals negative 3 or x equals 1. So the possible solutions to our rational equation is x equals negative 3 and positive 1. So after finding the solution, we need to check if our solutions are correct. So we will proceed to our step 5. So you now check each solution by substituting in the original equation and reject any extraneous roots which do not satisfy the equation. So by the way, extraneous roots are roots that do not satisfy the equation. Okay, let's substitute. X equals negative 3. So on the original equation. So 2 divided by negative 3 squared minus 1 minus 1 all over negative 3 minus 1 equals 1 half. Okay, let's simplify. So copy 2. Negative 3 squared is 9 minus 1. So it will be 2 over 8. Then 1. Negative 3 minus 1 is negative 4. Then it has a negative sign. So it will become positive. Equals 1 half. Then simplify this term. So 2 over 8 plus 1/4 is 1 half. 1 half equals 1 half. So the value of x equals negative 3 is correct. So it is a solution. Next, x equals 1. Okay, let's substitute the value of x equals 1 to the original equation. So 2 all over 1 squared minus 1 minus 1 all over 1 minus 1 equals 1 half. So it will become 2 all over 1 squared minus 1 is 0 minus 1 all over 1 minus 1 is 0 equals 1 half. So as you can see, 2 divided by 0 and 1 divided by 0 is undefined. So it will be not equal to 1 half. So therefore, in this case, x equals negative 3 is the only solution. That's why it is always important to check all solutions in the original equations. So you may find that they yield untrue statements or produce undefined expressions. So let us use problem number 2 in the previous activity to discuss and deepen your knowledge and skills in solving rational inequality. So the original rational inequality is 3x plus 1 all over x minus 1 is greater than or equal to 2. So step 1, put the rational inequality in the general form where greater than can be replaced by less than or equal to, and greater than or equal to. So r of x divided by q of x is greater than 0. So we transpose 2 to the left side. So it will become 3x plus 1 all over x minus 1 minus 2 is greater than or equal to 0. Step 2, write the inequality in a single rational expression on the left-hand side. So let us simplify. So it will become 3x plus 1 minus 2 times x minus 1 all over x minus 1 is greater than or equal to 0. So the simplified rational equality of this equation will be x plus 3 all over x minus 1 greater than or equal to 0. Take note. Remember that one side must always be 0 and the other side is always a single fraction. So simplify the fractions if there is more than one fraction. So the left side must be simplified and the right side should always be equated to 0 and copy the symbol. Okay, so after simplifying the rational equality, having the left side the equation and on the right side equated to 0, so we will proceed to step 3, which is set the numerator and denominator equal to 0 and solve. The values you get are called critical values. So this is the numerator part. So x plus 3 equals to 0. So the value x is equal to negative 3. For denominator, x minus 1 is equal to 0. So the value of x will be 1. The next step is plot the critical values on a number line, breaking the number line into intervals. So as you can see, we should need the values of the numerator, which is negative 3, and the value of the numerator, which is 1. So this is our number line. So number line is represented by numbers to the right, which is positive, and to the left, which is negative. So plot negative 3. So this will be our numerator, which is negative 3. And plot the denominator, which is positive 1. So this will be our critical values. After plotting the critical values on the number line, we will proceed to step 5. So step 5 is substitute critical values to the inequality to determine if the endpoints of the intervals in the solution should be included or not. So like in our rational equation, we will check if the critical values are included or not. Okay, let's substitute. When x equals negative 3 and when x equals to 1. Okay, so go back to our original rational inequality. So 3x plus 1 all over x minus 1 is greater than or equal to 2. Okay, let's substitute negative 3. So 3 times negative 3 plus 1 all over negative 3 minus 1 is greater than or equal to 2. 3 times negative 3, negative 9 plus 1, negative 8. Negative 3 minus 1 is negative 4, greater than or equal to 2. Negative 8 divided by negative 2 is positive 2, greater than or equal to 2. Okay, let's check if this rational inequality is correct. 2 is greater than or equal to 2. So, we need to say it is correct. And x equals to negative 3 is included in the solution. So, negative 3 is a solution. So, after that, we will find if x equals to 1 is a solution. Okay, so again, we will go back to the original equation and substitute the value of x. So, 3 times 1 plus 1 all over 1 minus 1 greater than or equal to 2. 3 times 1 is equal to 3 plus 1, which is equal to 4. 1 minus 1 is 0 greater than or equal to 2. So as you can see, 4 divided by 0 is undefined. So undefined greater than or equal to 2 is not a solution. So x equals 1 is not included in the solution. So after checking if the critical values is a solution or not, we will not now plot the critical values. So negative 3 is a solution. So it is represented by a whole field. And 1 is not a solution. So it is a hollow circle. Step 6, select test values in each interval and substitute those values into the inequality. So the original inequality is 3x plus 1 all over x minus 1 greater than or equal to 2. So in selecting test values, so you can apply any number which we will test later. So in this case, the values are -5, -1, and +3. So we will test those values later. So we select test values for the rational inequality. So we have x equals -5, x equals -1, and x equals to 3. So we should determine if it is a solution or not. Okay, let's substitute. So 3 times -5 plus 1 all over -5 minus 1 is greater than or equal to 2. 3 times -5 is -15 plus 1, -14 all over -5 minus 1, which is -6. So if we simplify this, it will become 7 over 3 or 2.33 greater than or equal to 2. So 2.33 is greater than 2. So x equals -5 is true. Next, when x equals -1, so substitute 3 times -1 plus 1 all over -1 minus 1 greater than or equal to 2. 3 times -1 is -3 plus 1 will become -2. -1 minus 1 is -2. -2 divided by -2 is +1 greater than or equal to 2. So x equals -1 is not a solution. So it is false. Next, when x equals +3, okay, so substitute again to the original rational inequality. 3 times 3 plus 1 all over 3 minus 1 greater than or equal to 2. So 3 times 3 is 9 plus 1 is equal to 10 all over 3 minus 1, which is 2. 10 divided by 2 is 5 greater than or equal to 2. So x equals to 5 is a solution, and it is true. So take note that if the test value makes the inequality true, then the entire interval is a solution to the inequality. And if the test value makes the inequality false, then the entire interval is not a solution to the inequality. So step 7, use interval notation to write the final answer. So the final answer is from -infinity to -3 is a solution, union with 1 to +infinity. So as you can see, so -3 is a solution represented by a closed bracket, and +1 is not a solution represented by open bracket. Lesson number 4, representations of rational functions. Rational function. The problem presented above is an example of rational function. To solve the problem, let us answer each question one by one. Below is the definition of rational function. Rational function is written in the form of function of x equals p of x all over q of x. It should follow the following conditions, namely, first, both p of x and q of x are polynomial functions wherein it has no negative and fractional exponents. Second, the denominator q of x should not be equal to 0. And third, the domain of all values of x where q of x is not equal to 0. So, we should ensure that the denominator is not equal to 0. If the denominator is equal to 0, then it will become undefined and cannot be considered a rational function. To further illustrate a rational function, let's have an illustrative example number 1. So first, define a formula for the average cost for every 5 days to stay in the resort function of x. To define the formula, use the formula in getting the average cost. Let the function be function of x. We can use the formula of getting an average. Average problem use the formula a equals x all over n, where a is the average, x is the cost, and s is the number of days. So let f of x represents the average cost per day and x represent the number in days. So note that 300,000 is a fixed price you need to pay plus the 700 pesos per day divided by the number of days x. We will have this rational function. So function of x equals 300,000 plus 700 times x all over x. So observe that it is similar to the structure of our original formula. Note that you will be using a formula depending on the classification of problems given to you. So some of our real life problems can be solved using the representation of our rational functions. So this is an example of a rational function. Illustrative example number 2. So for every 5 days stay in the resort, create a table of values showing the average cost. So in table of value, we have also two components, the x and y component, and its numeric data. So solution, make a table of values with x equals 0, 5, 10, 15, 20, 25, and 30. So from the table, we get y is equal to 0, 20,965, 41,930, 62,895, 83,860, 104,825, and 125,790. So from the table, we can observe that the average cost of stay decreases as time increases. We can use a graph to determine if the points of this function follow a curve or line. So as you can see, these values are being obtained from our rational function on the previous slide. We just substitute the values of x on the given equation. So from 0 to 30, and we get the y values, which is 0 to 125,790. So to further have a better understanding of this, we will have the graph of the rational function. So graph the following points in the Cartesian plane. So from the previous slide, we have the table of values. We will just plot the x and y values. So as you can see, this is the x and y values. So 0.1, 0.2, 0.3, 0.4, 0.5, and etc. So as you can see, by connecting the lines, we can clearly see that it follows a curve, thus a rational function. So a rational function can also be represented through a graph. Okay, let's have another example in graphing of a rational function. Okay, so this is the original function. So function of x equals to x all over x plus 2. So since we already have an equation, we can skip this part. Proceed with the table of values. So in this problem, we are already given by the rational function. So we will now construct a table of values from negative 2 to 2. So again, we will construct a table of values composed of x and the f of x. So from negative 2 to 2, we can have the x values for negative 2, negative 1, 0, 1, and 2. Then after that, function of x. So the function of x or y can be determined by just substituting the values of x from negative 2 to 2 to the original rational function. So the f of x values are first undefined, negative 1. So it will be negative 1 divided by negative 1 plus 2, which is 1 divided by negative 1 divided by 1, which is negative 1. Then 0 equals 0. For x equals 1, it will be 0.33. and for x equals 2, it will become 0.5. So we can observe that the value of x is undefined in when x is equal to negative 2. It is because when you substitute negative 2 in the function, it will have an answer of undefined, whereas in the definition of rational function, we cannot have a denominator equal to 0. Negative 2 plus 2 is equal to 0, which makes our rational function undefined. The next step is to plot the points in the Cartesian plane and determine whether the points form a smooth curve or a straight line. Okay, we have the rational function, we have the table of values. Now we can graph the rational function given the points in the table of values. So this will be the graph. So the 0.1, 0.2, 0.3, and 0.4. So as you can see, it can be observed that the function forms a curve. So it is a rational function. We will now proceed to lesson 5, which is about the domain and range of a rational functions. Domain and range. In definition, the domain of a function is the set of all values that the variable x can take, while the range of a function is the set of all values that y or function of x can take. So the domain represents the x values and the range are the y values. So domain are the inputs and range are the outputs. We can write domain and range in different formats. So we have 3 different formats. First, the roster format. Second, set builder form or notation. And third is the interval notation. So in roster format, this method enumerates the list of all values in the set. Example, the domain of R of t are 1, 1.25, 1.5, 1.75, and 2. By set builder form or notation, for example, in numbers 10 to 20, you can say that x such that x are even numbers from 10 to 20. So this symbol is read as such that x such that x, assuming that you also include odd numbers in the domain from 10 to 20, then you can write the domain of the function, which is represented by this set builder form or notation. So x such that x is an element of a real number. So element of a real number wherein x is greater than 10 or equal to 10 but less than or equal to 20. So x is less than or equal to 10 or less than or equal to 20. So next format is the interval notation. For example, in the function of x equals to 5 all over x minus 3, the domain of this function can be written in the form negative infinity to 3 union with 3 to positive infinity. This means that the values of the domain can take all the real values of x except 3, otherwise the function is undefined. So meaning to say, you can have all the real values from the negative infinity to the positive infinity except 3. Why? If we have the value of 3, so the denominator will become 0, thus the rational equation function will be undefined. So that will be the restriction. Okay, let's have an example to further understand the domain and range. So illustrative example number 1. Find the domain and range of the rational function. Function of x equals 2x minus 3 all over x squared. So first, we equate the denominator x squared is equal to 0. So therefore, the x value is equal to 0. So meaning to say the domain is that x such x are all elements of real number wherein x is not equal to 0, or simply x are all elements of real numbers such that x is not equal to 0. So that is all values can take the variable x except 0, because when the denominator becomes 0, the function of x will be undefined. Then for the range, we use the function of x equals y, so that we will now find the range. So we use the function of x equals y, so that y is equal to the function of x. So substitute y to f of x. So it will become y equals 2x minus 3 all over x squared. Then we do the cross multiplication. So y times x squared, it will become yx squared. Then copy 2x minus 3. Our next step is to transform the equation to ax squared plus bx plus c. So we will now transpose this 2x minus 3 to the left side. So as you can see, the symbol changed because we transpose it to the left side. So it becomes negative 2x plus 3 is equal to 0. So our new equation will be yx squared minus 2x plus 3 is equal to 0. So to get the solution, use this formula. So b squared minus 4ac greater than or equal to 0. So we have a value which is y. This is y. B value which is negative 2. And c value which is 3. So therefore, okay, let's substitute. So negative 2 times 2 minus 4 y times 3 greater than or equal to 0. So the new rational inequality will be 4 minus 12y greater than or equal to 0. 4 is greater than or equal to 12y. So therefore, 1/3 is greater than or equal to y. So in summary, the domain of x is equal to x. Such x are all elements of real numbers such that x is not equal to 0, and the range is y are all elements of real numbers such y is less than to 1/3. So as you can see, the symbol changes because we transpose y to the another side. So it will become 1/3. Illustrative example number 2. Find the domain and range of the rational function. So function of x equals x minus 2 all over x plus 2. So first we equate the denominator x plus 2 is equal to 0. Therefore, we get the x equals to negative 2. So our domain will be x such x are all the elements of R which x is not equal to negative 2. So we avoid using the negative 2 because if we use the negative 2, it will become negative 2 plus 2, which is 0, which makes our denominator 0, and it will become undefined. So the interval notation can also be written in domain is from negative infinity to negative 2 union with negative 2 to positive infinity. So it means that the domain are all real numbers except negative 2. So to find the range, we use the function of x equals to y, so that y equals x minus 2 all over x plus 2. So in solving this, you must multiply y and the denominator x plus 2 so that it becomes the equation on the next slide. So in solving this, you just multiply y and denominator x plus 2 so that it becomes xy plus 2y is equals to x minus 2. So xy minus x equals negative 2y minus 2. So we combine like terms, so x and x. Then 2y transpose to the right side, it will become negative 2y. So then we factor. So x times y minus y equals to negative 2 times y plus 1. So the value of x will be negative 2 times y plus 1 all over y minus y. So we simply divide both sides by y minus 1. And it will become x. So this will be the equation. So equate y minus 1 is equal to 0. So the value is y equals 1. So therefore, y is not equal to 1, otherwise the denominator is 0. So the range will be y such that y are all elements of range such that y is not equal to 1. That is, all values can take the variable y except 1 because the denominator becomes 0 and x will be undefined. So we should always consider that the denominator should not always be equal to 0. That will be the restriction of our domain and range. Illustrative example number 3. Find the domain and range of the rational function. Function of x equals to x squared minus 3x minus 4 all over x plus 1. So our first step is to equate the denominator x plus 1 equals to 0. So after equating, the x values is negative 1. So we transpose positive 1 to the right side and it will become negative 1. So the domain is x are all elements of real numbers such that x is not equal to negative 1. That is, all values can take the variable x except negative 1 because the denominator becomes 0 and the function of x will be undefined. So this will be the interval notation. So domain is from negative infinity to negative 1 union with negative 1 to positive infinity. In short, we can take all the values of x except negative 1 for our domain. Then, to find the range, we can factor first the numerator. So we can factor the original function of x in a factored form. So it will become x plus 1 times x minus 4 all over x plus 1. So you can cancel both x plus 1 of the numerator and denominator. So as you can see, x plus 1 is common to numerator and denominator. So we will now cancel. So it will become function of x equals to x minus 4. So function of x, we will change it to the value of y. So it will become y equals x minus 4. Then, we substitute x is equals to negative 1 to find y. So it comes from the denominator x is equal to negative 1. So let's have the substitution. Y equals the value of x, which is negative 1, minus 4. So y equals negative 5. So therefore, the range will be y are all elements of R such that y is not equal to negative 5. So in interval notation, so negative infinity to negative 5 union with negative 5 to positive infinity. So therefore, the range can take all the values of x from negative infinity to positive infinity except y is equal to negative 5.